Thanks for inviting me to this workshop, and welcome everyone to this virtual presentation on learning 3D reconstruction in function space. This is joint work with some of my PhD students, in particular Lars, Michael, as well as a collaboration with ETH, with Songyu, and Microsoft Research with Sebastian Novotin. My research group focuses at research at the intersection of robotics and computer vision. Our goal is to make intelligent systems more autonomous, robust, and safe. Intelligent systems must interact with a complex 3D environment. This is illustrated here by this video, where a robot might need to interact with such an environment that has complicated geometric structure and where accurate geometric reasoning is required to properly define affordances and to navigate through the scene. However, 3D reconstruction is actually a very hard problem, and it has been researched already since the 1950s. A traditional 3D reconstruction pipeline takes a set of input images, first computes the camera poses for each of these images using structure from motion or bundle adjustment, and then computes dense correspondences across these images, and for instance calculates depth maps that way, which are then fused into a coherent 3D reconstruction that can be further optimized using mesh refinement or volumetric techniques. Now, while most traditional 3D reconstruction pipelines require huge amounts of images for 3D reconstruction, humans can actually recognize 3D from a single 2D image. If I show you this image, you can easily tell me which object is in front of which object. What is the approximate distance to the refrigerator? Or what will happen if I will move forward? So the question I like to ask here is, well, can we learn to infer 3D from a 2D image as input? So this is the setting that we will consider throughout most of this talk. The input is a single 2D image, and then there is a neural network that tries to predict a 3D shape representation of that object that is depicted in that single image. Now, the input representation is pretty clear here. It's just a 2D RGB pixel matrix. But the question is, what is a good output representation? What is an output representation that can be easily predicted by a deep neural network, for instance? One of the natural choices for output representations are voxel representations. Voxel representations discretize the 3D space into regular grid cells, as illustrated here in the 2D and 3D examples on the right. Voxel representations were one of the first representations that have been proposed for the reconstruction task, as they are easy to process with neural networks, basically just requiring to generalize 2D convolutions to 3D convolutions. However, they have a qubit memory requirement, so the memory grows cubically in these 3 dimensions, and thus can only process outputs at limited spatial resolution. Furthermore, they incorporate Manhattan world biases, as one has to determine how this coordinate system that defines the voxels is chosen. Point sets are another representation that have been recently considered as output for neural networks. Point sets discretize the surface of the object into 3D points. They therefore do not model the connectivity or topology, and existing approaches are typically limited in terms of the number of points that they can process. Also, it's more difficult to encode local shape information, thus these point set generating networks typically require a global shape encoding as the context. And finally, also meshes have recently been used as output representations for 3D reconstruction using deep neural networks. Meshes are also discretizing space, but they are discretizing space now into vertices and faces. Existing approaches are also limited in the number of vertices and therefore the granularity that they can produce. And more importantly, they require either a class-specific template that is deformed, like a mesh model or a human body model that is deformed, or they are patch-based approaches that lead to self-intersections and non-watertight meshes, as in this example here of AtlasNet. And the reason for this is that meshes are just a very difficult output representation. It's very hard for a neural network to predict a mesh. In this work, we were wondering, well, is it actually really necessary to discretize space, as in all these three aforementioned representations that I've shown you? What we do in this work, instead of using an explicit output representation, is propose an implicit output representation that does not require any discretization. It can therefore model arbitrary topology and, in theory, at arbitrary resolution. It has a comparable low memory footprint and is not restricted to specific classes or categories for which templates are available. The key idea is very simple. Instead of representing the 3D shape explicitly, we instead consider the surface of the object implicitly as the decision boundary of a nonlinear classifier. Consider this neural network with parameters theta here that takes as input a 3D location, these are 3 coordinates, and a condition vector. This is a encoding of an image, for instance, like a 128-dimensional vector here. And it outputs an occupancy probability and therefore classifies if a point is either inside or outside the object. So in this case here on the right, if we apply this classifier to these points here, then the red points are classified as inside and the blue points are classified as outside. Or in this 3D example, we have this bench surface, and all points that are inside that bench object are the red points that should be classified with high occupancy probability, close to 1, and all the blue points should be classified with low occupancy probability, close to 0. I want to mention also there is some concurrent work. We have presented this last year at CVPR, and there were 2 very similar ideas that have been presented at the same conference. So how does our network architecture for predicting these occupancy values look like? Well, first of all, we have an encoder. The encoder depends on the condition that we want to use. Either we have a 2D image or a 3D point cloud or a coarse voxelization. And then the encoder simply produces a latent code, like a 128-dimensional latent code. And then we have a set of ResNet layers here that are conditioned on, in this case we use 5 ResNet layers, they are conditioned on this encoding and they get as input the 3D point location. And because we can do this in parallel on the GPU, we can input as many points as fit into GPU memory. In our case, we typically use about 2000 points. So t equals 2000 times 3 for the 3 x, y, z coordinates of the point that are fed as input to this network, processed all jointly, and the output then is for each of these 2000 points one value, which is the occupancy probability. This network can be trained using a very simple classification objective. We call it the occupancy network. The objective that we use is a simple classification loss, the binary cross entropy between the ground truth label. So we assume this is supervised learning. So we assume that we have the ground truth occupied label for each of the 3D points that we train with. And then we compare this to the prediction of the model f theta at that corresponding point location and given that image condition that corresponds to this label. And we do this for all randomly sampled 3D points in the mini batch. In practice here we use 2048 points in a batch during training. We can also extend this model to what we call a variational occupancy encoder, which is basically a VAE variant of our model. It's a generative model now, which doesn't need an image condition, but can be trained in an unconditional way. For doing so, we add an additional encoder that takes a object representation in terms of its points and occupancy labels and predicts a latent code, Q psi, which is then compared in this KL divergence to a standard normal distribution. And then we have also the reconstruction loss. Now, because it's an implicit representation, after training the model, we still need to, for a given image, extract the actual shape. The model doesn't directly return a mesh, but it just returns a parameter set for this neural network. So what we do is what we call a multi-resolution isosurface extraction, short MISE, which iteratively builds an octree by incrementally querying the occupancy network. How does this work? Well, we first start with a regular grid of points. Let's assume this is the shape that our function f theta represents. And if we query these points, we see that only one of these points is occupied, all the others are unoccupied here in cyan. Then we mark the voxels between the occupied and the unoccupied points as voxels for further investigation, and further subdivide these voxels and query these voxels again. We get something like this. So now we have these 4 inside points and the rest are outside points. And then we do this iteratively n times as long as we arrive, until we arrive at the desired resolution. Now this is of course much more efficient than querying the space densely, because we just need to query around the surface very finely. And then after having done this n times, we can apply the margin cubes algorithm to extract the surface from this, or to extract the mesh from these query results. And this entire procedure takes about 1 to 3 seconds in total, given a trained network. So let's have a look at some results. Here what we can see is the input 2D image on the left and the output of various baselines, a voxel baseline, point set generation baseline, a mesh generation baseline, and the proposed approach using the extracted mesh via MISE. On the left you can see the ground truth for comparison. So you can see our representation can handle complex topologies and results in smooth reconstructions. We can also reconstruct using a very sparse and noisy point cloud as input, where the goal is to predict a smooth and complete shape just from this representation as input. We can also use our model for voxel super resolution, where the input is a coarse voxelized representation of the shape that's encoded using a 3D network, and then we predict a fine-grained mesh from this representation. And here we show some latent space interpolations for the unconditional variational autoencoder model. We can see that novel shapes are generated that were not part of the original training set. Okay, so that's nice, but can we also learn about object appearance? So far we're just talking about object geometry, right? Can we also learn object appearance? In ICCV, we've proposed an extension of the previous model that applies essentially the same idea to predicting the texture. In this case, the input is a 3D model, a Vercat model, or a model predicted using an occupancy network, as well as a image, which is the condition. And then we have what we call a texture field that for every point on the surface of that object predicts the corresponding color value at that point, which allows us to render texture 3D models from this geometry. This is what the model looks like. We have, again, a regular image encoder that gives us a low-dimensional latent code C. We also encode the input 3D shape, in this case using a PointNet encoding into a global shape encoding S. And then we render this 3D shape into a depth map in order to query 3D points on that surface by just unprojection through the camera matrix. So that for every pixel that corresponds to that depth map, we can then get the 3D point and query what they call texture field for the color value. The texture field gets the 3D location as input, the shape encoding, and the image encoding, and predicts a RGBD color value. And we train this using a reconstruction loss. We can also build generative versions of this model. So one thing that we did is we used a GAN or adversarial loss, where now there is no image encoder anymore, but we sample the latent code randomly from a standard normal distribution. And here we have no reconstruction loss, but instead we compare the predicted and the true image using this discriminator. We can also build a VAE type of model where we now have the reconstruction loss again, but we also have an encoder that takes an image and predicts a latent code for that image that gets reconstructed and then compared to the original image using the reconstruction loss. So let's look at some results. The first thing that we investigated was the representation power of this model. What you can see here for two examples, on the left is the ground truth, and then the overfitted result of our texture field approach and a simple voxelization of the object. You can see that we retain fine geometric detail for smoothing out some of the fine structures here on the cat, for instance. This was overfitted to each of these two objects individually, but we can also overfit our model to multiple objects simultaneously. So in this case, we have overfitted to these humans here simultaneously. So now let's look at some prediction results. What we have here are single image texture reconstruction results, where on the left we have the 2D input image, and then we have the results of a 2D novel view synthesis baseline and our texture field approach. The novel view synthesis baseline has a really hard time in this 2D to 2D translation task here. So it doesn't lead to very consistent results, while our results are consistent by definition and also have fine details. Still, you see that the texture is somewhat over smooth in some of these results. Here what we did is basically took a real image roughly corresponding to a CAD model and showing that we can also predict the texture based on real images, not just on rendered images of the same object. Here are some results when combining this with the occupancy network geometry prediction. So here both geometry and texture are predicted. Finally, here are some results of the generative model. We show some latent space interpolations, in this case the same appearance code for different geometry encodings. Okay, so another thing we were wondering is, well, now since these implicit representations seem to work somewhat okay for geometry and appearance representations, can we also use them to represent 3D objects in motion? So now instead of representing the shape at one time instance, we want to represent the shape at every point in time. However, extending the occupancy network idea directly to 4D is really hard because of the curse of dimensionality. And this will be visible from the video I show you in a second. What we do instead is to represent the shape only at a single point in time using a 3D occupancy network that can recover fine geometric details, but then represent the motion by a temporally and spatially continuous vector field. And that's easier than representing the entire 4D geometry. because this motion field is much smoother compared to representing the geometry. Now, in order to model this, we need to model the relationship between the 3D trajectory through this velocity field and the velocity itself. And this is, of course, defined by a simple ordinary differential equation, which simply tells that the derivative of the location is equal to the velocity. And what we use is some recent advances in differentiable ODE solvers to incorporate this into our model. Here's an illustration of the network architectures. Now, in comparison to what we had before, we have multiple point clouds or multiple images as input, which we simply concatenate and then use similar point net and 3D convolution architectures to get a global encoding of this motion sequence. Here's an illustration of the approach in general. Here on the right, you can see at time equals tau, a ground truth object. And then you can see here that this object is deformed in our model through time, such that this left arm, for instance, moves here downwards at time t equals 0. And we can solve this ODE differentiably. Our model predicts then the occupancy at time equals 0 and the velocity field at all continuous time instances. And in order to apply the reconstruction loss, we simply take this point, we pass it through our neural ODE solver in order to obtain the occupancy value. So basically, this point maps to this point here. We get the occupancy value of the reconstruction model at time equals 0, and then we can compare this occupancy value to the true occupancy in our observations. The nice thing is that we can train this model based only on a reconstruction loss. This is the loss that I've just shown you on the previous slide, where we take basically the true occupancy value and the predicted occupancy value of our model, which takes a point and passes it to time tau for a given image condition x. But we can also use a correspondence loss if we know correspondences explicitly. So the correspondence loss here is really optional, and the correspondences are implicitly established by our model. If you have correspondence information available, you get better results, but you can also get correspondences implicitly by just using a reconstruction loss. So let's look at some results. Let's first look at some point cloud completion results. Here on the left, we have the input, a very coarse and noisy point cloud sequence, the result of a point set generation network, and our occupancy flow results. In comparison to a naive extension of the occupancy network idea to 4D, which loses a lot of geometry, we can retain a lot of detail through this occupancy flow idea by not suffering as much from the course of dimensionality. Here are some examples for reconstruction from image sequences, which is, of course, a very hard task. Okay. Now, all of the models that I've shown so far were using full 3D supervision. For each point in space or in space and time, we had to know the occupancy value. This is inconvenient because often there's no such 3D supervision information available. And there's much more data for which this information is not available than there is data for which it is available. And there is, for the classical explicit representations, differentiable rendering algorithms available which allow us to learn these representations from 2D supervisions, only from RGB images, instead of having access to this 3D supervision. And the question we were asking now in a paper that's presented at this CVPR is, can we actually learn these implicit representations also from images, from 2D images alone? The architecture we use here is actually even more elegant than the architecture that we had before, because it combines geometry and appearance prediction. Again, we have an image encoder that takes a 2D image and produces a global latent code for that image. And we have a set of points that we pass through the network simultaneously. And then we have 5 residual blocks here that are conditioned on that image. And we have a shallow head that predicts the occupancy probability for each of these points, and another one that predicts the texture, the color information for each of these points. So both of these heads are applied to the same backbone network here. Now, in order to define a differentiable rendering algorithm in PyTorch, we need to, of course, define the forward and the backward pass of the network. The forward pass corresponds to the rendering pass. The forward pass is relatively simple. So we see here on the right a simple bird's eye view demonstration or example of the situation that we look at. We have an image plane, we have a camera center, we have a ray that's defined by the pixel that's oriented in direction W. And then here in 3D, we have represented the occupancy network by these 3 curves here, where the thick curve corresponds to the surface. This is where f theta equals tau. This is the decision boundary of the classifier f. And here we have, for instance, points that are behind the surface and points that are in front of the surface. What we do now for rendering is that we go through all the pixels in the image and find the surface point we had along the ray W via ray marching and route finding. So we first look at equidistant intervals of points along the ray, and once we find a change in the sign here, then we do route finding in order to retrieve that exact point in a small number of queries of the occupancy network. We then evaluate the texture field T theta at this predicted surface point P hat and insert that color value at that corresponding pixel location. Doing this for all the pixels, we get the entire image. Now, how can we define the backward pass differentiably? In the backward pass, what we want to do is we want to compare the prediction I had to the observation, the observed image I. As you can see here illustrated, these two don't match exactly. So the prediction of the model currently is not exactly corresponding to the observation. There is a reconstruction error. So what we want to do in order to minimize this error is we want to minimize a loss function, for instance, a L1 or L2 loss between the prediction and the observation. And we can do that by simply computing the gradient of that loss with respect to the parameters theta. So we do this by computing the gradient of this loss using the chain rule, which requires us to computing the derivative of the predicted image with respect to the parameters. This derivative is equal to this total derivative expression here, because both the texture field as well as the predicted point location depend on the parameters theta. Now the question is, how can we actually compute the predicted point location that depends through this ray marching algorithm on the occupancy network? How can we compute the derivative of this point with respect to the parameters theta? And we do this by using implicit differentiation of this constraint here. And the constraint is the constraint that we have had before, which is simply saying that the occupancy network should predict at that particular point tau, which corresponds to the surface or to the decision boundary. So if we do implicit differentiation of this expression, we get an analytic expression for this derivative here, which is nice. So what I've highlighted in red here are all the terms that depend on the parameters theta. So we have the texture network here and we have the occupancy network here. And so what we want to do now is we want to update these parameters such that the reconstruction loss here decreases. So maybe like this. So we have the constellation before, where both the occupancy field and the texture field are in this state, and now both of them change. So both the texture changes and the occupancy field changes. This is nice. We have found an analytic solution, and importantly, in comparison to differentiable rendering algorithms for voxel-based representation, which require ray marching along the voxels, we do not need to store intermediate results along these voxels. So the method is also quite memory efficient. So let's have a look at some results. Here on the left, we can see the 2D input image and then the result of a baseline method, soft rasterizer using 2D supervision, pixel to mesh, which actually uses 3D supervision, and our results using only 2D supervision. Or what we can also do is we can add depth maps as supervision using this differentiable renderer. So these are the results using also depth information, which of course makes the problem easier. Here's an example for a car, the results of soft rasterizer, pixel to mesh, which uses 3D supervision, and ours, which uses 2D supervision only. Or here with 2.5D supervision. What we also did is we looked at multi-view reconstruction. Here we used the DTU dataset just to demonstrate that this approach also works for real data. And we were overfitting the model to single instances, to single objects, based on a set of images of this object. And you can see the reconstruction result here. Even though the images are not covering the object completely, we can see that the reconstructions are quite complete and also quite accurate. This is a benefit of this approach, which by definition yields watertight meshes. Here's an illustration of training progression over time. You can see it flickers a little bit because of the stochastic optimization approach. Great. Now, in the last couple of minutes, I like to show you a few more recent results, which are not all from our research group, but also from other groups in the fields of these highly dynamic fields of implicit shape representations. So one work that I like very much is from Lippmann et al., who proposed this universal differentiable renderer for implicit neural representations. The work is quite similar to our DVR model that I've shown you on the previous slides, except that they also consider now the normal and the light location. So we basically model the physical image formation process using the rendering equation, which you can see here on the bottom, where this shape representation is still represented by this neural implicit function. And the nice thing, of course, also about this shape, by modeling this shape using implicit functions, is that normals can be retrieved quite easily. This is a project that we were doing recently in my group, where we are trying to apply this idea of implicit representations to modeling surface light fields. Surface light fields are stronger or more powerful than just text representations because they can model the appearance depending on the viewpoint. What we have here is, again, an image encoder, which produces an image encoding C, a shape encoder that produces a shape encoding S, and then we have what we call an appearance field that takes a 3D point and the shape and image encoding and produces something that's a little bit like a material representation for each of these 3D points. And then we have a lighting model that takes this material representation and a view direction and a light setting and predicts the color at the particular 3D point. And then we train this using a reconstruction loss on a data set that has realistic materials. Here are some results of this model. So we first look at how well can this model actually model shadows. You can see on the left our results, on the right the ground truth, and you can see that it can model shadows of the object quite effectively by representing them as this neural network. It can also cope with reflections. So here we have modeled a highly reflective object with such an environment map, and you can see how these reflections move over the surface of the object. One difficulty with applying this model is that we need to have access to data sets where the light source location is known or the environment map is known. That's why we use mostly synthetic data for demonstrating the technique. Here's a comparison to a simple image-to-image translation baseline, which of course cannot deal with neither the appearance nor the surface light field well. This is for changing the light location. And now here are our results. When changing the viewpoint, you can see how the specular highlights move over the object. And you can see what happens when changing the light location. Another thing we recently did is looking into the 3D representation itself. One fundamental limiting factor of these occupancy networks is that we use a very simple, fully connected residual network that takes a global shape, global appearance encoding, global encoding, image encoding, and then produces an occupancy probability for each of the 3D locations. So this is limited because this fully connected network is not expressive enough to handle scenes of that size here. This is an example from the Matterport dataset that contains many rooms of a building. What we did therefore is to combine this idea with the idea of a convolutional 3D neural network. Instead of having a deeper fully connected network, we have a more shallow fully connected network, but then have a 3D network that operates on a coarse voxel grid. And this fully connected network then queries features by interpolating the features from this 3D voxel grid. So we have first 3D convolutions to generate a 3D feature volume. Here the dots are the centers of the voxels. And then for a 3D point, we query the features using interpolation. And this leads to models that can reconstruct even very large spaces very well. A similar idea, but not for 3D convolutions, but for convolutions on the 2D image space, has been proposed in PyFu, where a 2D convolutional network operates on the image domain, and then the 3D points query the image depending on where the projection of the 3D point falls into that image. And they get quite nice reconstructions, both in terms of geometry and in terms of texture representation. Again, these results are predicted from a single image as input. You can also integrate multiple views and you get more precise results on the back of the model. This is a work by Tom Funkhauser's group where they combined the idea of implicit representations with primitive-based shape models. Here, each of these ellipsoids corresponds to one part of the object, and each of these parts is modeled with its own shallow, call it a tiny occupancy network, so shallow implicit representation. By combining all of this into a model, you get very precise shape that is now more controllable because you have now these little control elements here. Each of these parts corresponds to one of these ellipsoids. And this is very recent work called NERF, representing scenes as neural radiance fields. They also use an implicit representation, but not an occupancy network or a signed distance field, but instead we use volume, a representation that is can be rendered using volume rendering. So they basically represent the color and the density, the volume density at every 3D point in space using a neural network that's dependent on the location, the 3D location of the point, and the viewing direction. So they can also model view-dependent appearance changes. And then they overfit this model based on hundreds of images of onto single scenes and use it then to do novel view synthesis by basically, for a novel viewpoint, integrating the color values and the density values along the ray. So here are some results that they obtained with this model in comparison to some novel view synthesis baseline on the left. Quite exciting, as this model seems to be able to handle very fine geometric details quite well. It doesn't only work for single objects, but it also works for entire scenes. The model leads to much less occlusion artifacts as previous novel view synthesis baselines. And finally, I want to show where these models have also been used in the 2D domain. This is work is called point rent image segmentation as rendering, where in 2D segmentation corresponds to basically what reconstruction corresponds to in 3D. They use a similar idea as occupancy network to improve the results of mask RCNN by having a occupancy network head that can then be queried to refine the boundaries. The problem of mask RCNN is that the output resolution is typically very coarse, so it cannot capture these fine geometric details such as the fingers of the hand, while if you model these details using this neural network representation on top of it, you can get much more fine-grained details for this shape. So this is all very exciting. I want to conclude now my talk with this little summary. Neural implicit models have emerged as a very effective output representation for shape, appearance, materials, motions, and more. They don't require any discretization and they can model arbitrary topology. And they can also be effectively learned using 2D supervision. And there's many applications: 3D reconstruction, view synthesis, segmentation, motion estimation, and more. However, they also come with a number of challenges. First of all, for the occupancy network, the geometry must be extracted in a post-processing step, which requires between 1 and 3 seconds. Also, the extension to 4D, as we've seen, is not straightforward due to the course of dimensionality. Furthermore, the simple fully connected architecture and global conditioning lead to overly smooth results. But there are some promising research directions, like using local features as in the convolutional occupancy network that I've shown you, or in PyFu, or to use a better input encoding that NERF uses, for instance. That's all from my side. I want to thank you very much for listening. I want to thank my sponsors for supporting our research, and I want to point you also to this website. We have a little website where we host a blog and present our latest research results. Thanks.